Good afternoon, everyone. Welcome to the next QSimFP webinar. This talk will be given by Laura Sberna from Albert Einstein Institute in Potsdam, Germany. But Laura will join us very soon at the University of Nottingham as a Marie Curie and Nottingham Fellow working in mathematical sciences. So this talk will be on nonlinear effects in the black hole ringdown. And without further delay, I would like to give floor to Laura. So please.
Thank you. Thanks everyone for joining and for inviting me for this seminar. So before diving into nonlinear effects, let me first give you some introduction on black hole perturbation theory and the general problems we are trying to tackle. So black hole perturbation theory is a tool that we use when our problem can be approximately described by a black hole solution of Einstein's equation with some small perturbations. And the prime example of a problem of this type is indeed the black hole ringdown. This is the final stage in gravitational wave events that we have already detected with LIGO and Virgo, because when the two binary components, black holes or even neutron stars, merge, they eventually form, if not a neutron star, almost always a black hole, and this black hole is still perturbed by the dramatic event it went through, and therefore needs to ring away, as you can see in this numerical relativity simulation. It needs to ring away its perturbations until it settles into a final equilibrium. And in more technical terms, indeed, to do black hole perturbation theory, we assume that the zeroth order solution is a black hole solution. For example, the stationary axisymmetric Kerr black hole for a spinning black hole. And then we assume that the metric or whatever other field we have in our problem can be described by that solution plus some small perturbation. And we expand our equations of motion until we find an equation for these linear order perturbations. And in the case of gravitational perturbations of Kerr, this is the form that the first order equation takes. So it's a wave equation with some other terms that I'm not writing down explicitly, because really this wave-like structure is what matters in determining, well, together with the potential, is what matters in determining these special solutions that are the black hole modes. So this equation admits a discrete spectrum of modes known as quasi-normal modes with these frequencies omega n, L, and M. And so what are these modes? When we look at the black hole from far away, the time dependence of this mode is very simple. They're oscillating over time with the real part of this frequency spectrum. But they're also decaying exponentially, and this decay is determined by the imaginary part. And the existence of this imaginary part, the fact that the spectrum is complex, is ultimately associated, due to the fact that the problem has some dispersive nature. So the perturbations can fall into the black hole horizon, and they also emit towards infinity. The overall spectrum, though, has some very nice property. It's only determined by the mass and the spin of that final black hole, of the black hole that we're using in our zeroth order solution. And you can already imagine that this means that we can use these modes to infer the properties of that black hole in gravitational wave observations. But we can also do more and test general relativity, which predicts this unique spectrum. Overall, the signal of that perturbed black hole can be, of course, written as a superposition of all the modes in the spectrum with some amplitudes and phases that depend not on the, these unique properties of the black hole, but unfortunately do depend on the initial conditions. So in the case of binary mergers, they depend on the properties of the binary that eventually formed, through the merger, this single black hole. Okay, so this was a short summary of black hole perturbation theory at linear order. So next, I want to motivate why in the past few years, there's been a lot of interest in going beyond this linear order in perturbation theory. So why do we need to go beyond linear order and make our life harder? Well, one motivation, as I said, is that we use this linear model to infer the mass and the spin of the final black hole in gravitational wave events, and in general to match our gravitational wave models to observations and infer the properties of the system. And on top of that, we use this linear model to test general relativity. And I think it's fairly intuitive to understand that, for better tests, we also need more accurate models. In particular, if this is the ring down in a gravitational wave event, if we want to model accurately the signal at early times, we need to use more modes. At late times, some of the higher modes in this, spectrum number n have already decayed. But if we want to also accurately model this early phase, we need more modes, as you can see. But if the modes at early times have larger amplitudes, we might lose accuracy in our first order modeling, and we might need to go to higher orders in perturbation theory. Another reason within the black hole ring down is a specific limit of the system, which is the near extremal limit, when the spin of the black hole is close to the extremal case. So A would go into 1. This is because in this limit, we know that there's instabilities. Exactly, extremal black holes have the so-called Aretakis instability. But even in the near extremal limit, not quite extremal, if epsilon down here is the extremality parameter, you can see that some modes in the spectrum take on a very special form, where their imaginary part is very small. So these are very long-lived modes. And also they have, this special imaginary part that depends on the angular number m. And so this means that the spectrum is in somewhat commensurate. So two modes in the spectrum could be combined to give a new mode that still belongs to the same spectrum. And you can imagine this to give rise to interesting nonlinear interactions that might accumulate energy, in a certain direction in frequency towards perhaps higher frequencies, and lead to something similar to turbulence in fluids. What you see on the right is a simulation in ADS spacetimes, so with a different asymptotics compared to asymptotically-flat black holes. And it's not known at the moment whether realistic astrophysical black holes could develop this turbulence or any other interesting nonlinear effect due to this near extremal property. Another reason to use black hole perturbation theory beyond linear order is to try to tackle perturbatively problems like computing the modes, but beyond general relativity. You can imagine treating your deviations from GR as perturbations in your problem. And these in the figure, for example, are various quasi-normal mode spectra, varying with the color, as we vary the mass, if we make the graviton massive. And similarly, you could use black hole perturbation theory to go beyond vacuum. So for example, if you have even minimally coupled scalar field that has, for some reason, accumulated around the black hole, you could treat its present and its effect in a perturbative way. So I hope I give you some motivations to look at black hole perturbation theory beyond linear order. I think in a second we will see some more from recent analysis of numerical relativity simulations. But first, let's look at what we know so far about, at the very least, the next order in perturbation theory. So a second order in perturbation theory, we have kind of an extended version of the Tchaikovsky equation, because we know that the second order perturbation, this psi2, satisfies an equation that is similar to the first order one. You can see on the left-hand side, we have that same Tchaikovsky operator that I've summarized with this curly O. But now on the right-hand side, we'd have a source that is a combination of two first-order perturbations. So what do we know about this source? We know it's, I could write down the expression, is a bit complicated and not particularly illuminating, but we've known what this source looks like for a long time. And we've also explored, people have explored this equation numerically and with some approximate analytic techniques, at least in Schwarzschild. But most interestingly, people have found, signs that the second order perturbation is excited in numerical relativity simulations of binary mergers. So in particular, what they've seen is that, maybe it was on the previous slide, that this source, you can expect it to give rise to these kind of quadratic interactions, right? Where the angular number m gives rise to this m plus m prime mode, and also frequencies combine in a linear way, right? Because you're going to have these exponentials e to the I m phi and e to the minus I omega t. And so what people did was look into numerical relativity simulations and see if they found these special combinations of frequencies that do not belong to the linear ordinary spectrum. For example, if you originally had excited the 220 modes, where this is L, M, and N, the three quantum numbers of quasi-normal modes, you can imagine at quadratic order, giving rise to a sum of these two frequencies, so twice the original frequency. People were able to identify this special frequency in these simulations. So this was actually one of the first clear identification of a nonlinear effect in the ringdown, of course, in simulations and not in gravitational wave data, because data is not, the signal to noise ratio is not high enough at the moment for this to be visible in gravitational wave data. So another effect that you can find beyond linear order is an adiabatic frequency shift. Let me explain what I mean. So in these numerical relativity simulations, we find quite generally that even once a common apparent horizon has formed, so that final black hole has formed, its mass and spin are still evolving a bit at the beginning of the ring down as a function of time. And this is not surprising, because I told you at the beginning of this talk that quasi-normal modes need to have this influx through the black hole horizon. And so these modes are depositing some of the mass and angular momentum that was sitting outside into the black hole and causing this mass and spin evolution. And we see this pretty generically in numerical relativity simulations. So this is an histogram over the catalog of the SXS collaboration. And as you can see, this is usually a 10% effect in most simulations, but it can, vary with plus minus 5%. So what happens when, what we used to think of a, constant background black hole with a fixed mass and spin, what happens if that background instead is slowly evolving in mass and spin? Well, there's been some studies in some simplified settings that show that frequencies should follow adiabatically this mass and spin evolution. So what I plotted here with this assumption in mind is the frequencies that I would expect to see in the ring down as a function of time.
Hi, Laura, sorry, can I interrupt you? I think Silke has a question. Silke?
Oh yeah, sorry, it was up here, I don't see it. Okay, now I lowered it, I didn't see the hand. Go ahead.
Laura, would you mind going back to the previous slide?
Yes. This one.
The distribution where you said you had a frequency shift. I don't understand where you get the distribution from, because you have classical simulations. If you fix the same initial state.
No, this is for simulations with different initial states.
Ah, okay.
Yeah. It's just meant to represent what would happen across a population of gravitational wave events or observations.
Okay, thank you. That makes sense. Thank you.
Yeah, so as I was saying, we do expect, at least in this adiabatic approximation, to have frequencies evolve with time, especially at the beginning of the ring down, and again with the, a shift that is of order 10%. So this is the setup, that the model, the extended nonlinear model that you should have in mind. It's a model in which, our modes are still combined with some amplitudes and phases, but their frequencies now are evolving with time due to the mass and spin evolution. And of course, if you're only interested in a late time signal, this part in orange, the mass and the spin have already settled to their constant final value. But if you were interested in the earlier part of the signal, then you would be more sensitive to this evolution. And this is something that with Pablo Bosch, a colleague from Utrecht University, we're trying to demonstrate, and we think we have demonstrated, but the paper will come out maybe in a month or two. We're trying to demonstrate that this effect is visible in these numerical relativity simulations. One last nonlinear effect that I wanted to mention was some work from a few years ago, where we look at a third order effect, but not in gravitational perturbations, rather in scalar perturbations, which are a little easier to simulate. And indeed, in that case, we were able to do very simple simulations where we had a black hole, and we set up some initial data outside the black hole that perfectly matched, or as perfectly as you can, a given mode in the scalar field spectrum. In this case, it was an n=1 mode, so an overtone of the spectrum. So as you can imagine, the scalar field at initial times is simply decaying, also oscillating, but here we're taking the absolute value. It's simply decaying following, the imaginary part of the frequency of that mode. However, at late time, we are able to see the effect of this cubic interaction in the scalar field perturbative scheme. where you're able to mix two first-order modes to give rise to a mode, in this case, still belonging to that same spectrum, but with a different overtone number. And the nice thing about this setup is that, of course, this nonlinear effect is very small. So if you prolong this line at early times, this had an amplitude that was 2 orders of magnitude lower the linear order mode, the dominant mode. However, because these modes have different decay times, if we wait long enough, the dominant mode is eventually going to drop below this third order mode. And we're able to see it in this setting. Okay, so we've reviewed the signs kind of nonlinearity in numerical relativity simulations, and also the motivations to look for these effects. But so far, we have not made a lot of analytic or semi-analytic progress in describing these effects, except maybe for their frequency dependence. So with my collaborators, we started wondering if we could use quasi-normal modes themselves to make progress at higher orders in perturbation theory and do some mode expansions at higher orders. Unfortunately, to do this, there's a few obstacles, because quasi-normal modes are not quite normal modes that we're used to dealing with in, for example, quantum mechanics in a box. Because these modes do have a discrete spectrum, but have this decaying property. And also, it's not clear whether they're orthogonal under any inner product, except maybe for some result in the 90s for modes of Schwarzschild that didn't get a lot of attention. And another complication is that while normal modes are usually a complete basis, complete orthonormal basis, quasi-normal modes are not complete, because we see this, whenever you put some initial data and solve the Tchaikovsky equation, your perturbation that comes out as a function of time has two pieces that are not describable in terms of quasi-normal modes. A first piece is the direct emission coming from that initial data and propagating to the observer. And the second piece in green here is a late time tail that doesn't have the oscillatory and exponentially decaying behavior of quasi-normal modes, but instead is power law and not oscillating. So, but if we set aside for a moment at least this final complication, let's look again at the question of whether quasi-normal modes are orthogonal, at least. Well, as I mentioned, that this was not quite understood until a couple years ago, especially thanks to Stephen Green, Peter Zimmerman, and Stephen Hollands. We were able to find a right product, under which quasi-normal modes are indeed orthogonal. And I know that this is a bit of a cryptic expression, so let me unpack it a bit. So what we are given two quasi-normal modes, I'm calling them psi1 and psi2. What we're doing here is an integration over a spatial slice of the conserved current associated with my, Tchaikovsky equation. This is, you can think of it as just a generalization of the conserved current for the Klein-Gordon equation. And the other ingredient here is that I'm not taking directly the two quasi-normal modes, but I'm doing a T5 reflection of one of them. So I need to use, this important symmetry of the Kerr solution. If you're familiar with this, this T5 reflection is used to go from the Tchaikovsky operator to its adjoint. And again, if this was still too cryptic, this is the product written out in Boyer-Lindquist coordinates. And as you can see, this is not a simple product because it involves some time and phi derivatives of the quasi-normal modes. But all of these complicated ingredients were kind of engineered to give the product the right properties to find the quasi-normal modes are orthogonal. So one of the key properties is that this product, as we've written it, is symmetric under the time translation operator. So you put it on the left or on the right, you get the same result. And this is the property that gives you the orthogonality of the quasi-normal modes, because this time translation operator is nothing other than a t derivative. And so it brings down the two frequencies of the modes. And it tells you that they must be orthogonal or their norm must be null. So we have demonstrated that quasi-normal modes, despite all their problems, are at least orthogonal. And this is actually true for other black hole modes. For example, when you have a scalar field with a mass, you can have other types of modes that are quasi-bound, so they decay towards infinity in space, and so they're kind of bound around the black hole. And these are particularly interesting modes because once they're bound and once the black hole is spinning, they can also become unstable, and so they don't just decay over time, but they grow. And this is how you can generate these nice clouds of scalar fields or other bosonic fields around black holes. Interestingly, these modes admit a very simple limit when the mass of the scalar field is small, because their equation starts to resemble the hydrogen atom, Schrödinger equation. And so in this limit, with this simple analogy, you can derive the spectrum and the mode radial functions. And in this hydrogen atom limit, you wouldn't be surprised to find that also these different types of black hole modes are orthogonal for different frequencies. And indeed, we were able to extend our product to the massive scalar field case, and we found that also these modes are orthogonal. So finally, now that we have that are modes that appeared in the linear spectrum, so that seemed, so conveniently available to us to do perturbation theory, like in quantum mechanics. Now that we know that these modes are at least orthogonal under this new product, can we use them to do perturbation theory beyond linear order? Well, let's try to understand this in a simple example. So let's say I have my Klein-Gordon equation for a scalar field phi on a black hole background. And let's say I have added to this equation some perturbation in the potential, in this case, delta V. And we want to try and do perturbation theory, so understand the effect of this extra potential using our modes, our orthogonal quasi-normal modes, or quasi-bound modes. So we're going to write the full solution with a mode ansatz, so as a superposition of modes, but with some time-dependent coefficients. This is just what you would do in quantum mechanics. So we're going to introduce this mode ansatz into our equation, and then we're going to project the equation onto one of the modes, say phi n. And so this is what the equation looks like at the moment. Of course, we would like to act with our Klein-Gordon operator in this case on the coefficients and on our modes. Of course, the modes will give 0 because they're solutions of the unperturbed operator. And we would then like to take the coefficients outside of the product. Unfortunately, these steps are not so straightforward in this generalization of our quantum mechanics perturbation theory, because if you remember, the product also contained some derivatives. So you need to be careful when taking time-dependent things out of the product. But if you assume that the coefficients in this expansion are slowly varying with time, and you use the orthogonality of the modes, then you can reduce that equation to a simple formula for the evolution of these coefficients, C of n. And if you remember your quantum mechanics lectures, either as a student or as a lecturer, you must remember that in quantum mechanics, these time-dependent perturbation theory equations take a very similar form. So that's great. For an even simpler example, you could do time-independent perturbation theory, in which the perturbation is written in terms of a perturbation in the spectrum, in the frequency, and a perturbation in the, say, radial mode function. Well, in this case, also, this black hole perturbation theory in terms of modes gives rise to an equation that is very similar to quantum mechanics. You know, this gives you the deviation in the frequency due to this potential deviation delta V in terms of this diagonal element of the matrix of the potential acting on the modes, and just some normalization condition at the denominator. So we, of course, this is all very abstract, but we wanted to test this equation on some simple example. So we went back to that super radiant cloud that I mentioned before, a mode that is kind of confined around the black hole and is growing over time exponentially. For this mode, we can compute the Newtonian potential and try to understand if the self-gravity of the mode has some effect on its frequency, right? Because usually modes are computed on the black hole background without taking into account the back reaction of the mode itself. But with this perturbative scheme, we can compute the effect of this self-gravity. And this is the result that we found. We were able to get these red dots that you see on the plot on the right, and that, as you can see, are pretty close to the result obtained this year also using numerical relativity by the group at Perimeter Institute. So I'm showing you this, basically the frequency drift. It doesn't really matter that we have all these other quantities in the y-axis, but so I'm showing you the frequency drift really, you know, as a function of the mass of the cloud, or divided out by the mass of the cloud, and as a function of the scalar field mass. Because I told you earlier that these modes have a simple limit when the mass of the scalar field is small. It's this hydrogenic limit in gray. So we can see that our method reproduces these results, hydrogenic results, when the mass of the scalar is small. But it does a better job when the mass of the scalar is large, because we don't need to make this approximation, except perhaps in computing the potential, where we do assume that we are kind of in Newtonian gravity almost. Okay, so I've come to towards the end of the talk. Let me just summarize, because I know it was a lot of ingredients that went in. So I've given you a few reasons to go beyond linear order in black hole perturbation theory, both as, you know, kind of general theoretical motivations, and also because we do see these departures from linearity in numerical simulations. Unfortunately, I cannot tell you yet whether and when these deviations will be needed to confront actual gravitational wave data, but with new gravitational wave observatories coming up in the near future, we think this going beyond linear order is going to be necessary, at least for some events. And I think there's, as I mentioned, there's more broader applications of these methods, perhaps also in understanding, analog simulations of black holes. And so the new tool that we're trying to develop and that we have developed recently is, an orthogonal set of modes with which we can build a perturbative scheme to tackle these nonlinear problems. And at the very end, I've given you a first application of this method that seems to work fairly well. And that's it. Well, that's it.
Okay,